meeting is being recorded.
Oh, that's a fun noise. All right. Welcome to Crafting Interpreters in Rust, session whatever, 18, I think. We are about to start reading chapter 8. I think because we're still sort of fixing all the little problems in the parser. We're passing some test cases now, but there's still some problems in the parser. I think we'll read and then go back and revisit how to do the stuff in chapter 7 and 8, which is interpreting expressions, he tells you, and throwing runtime errors and stuff. Once that's correct. So I'll start reading here. So chapter 8, statements and state. The interpreter we have so far feels less like programming a real language and more like punching buttons on a calculator. Okay, so it looks like he's gonna tell you how to interpret additional things beyond expressions. Yeah. Programming to me means building up a system out of smaller pieces. We can't do that yet because we have no way to bind a name to some data or function. We can't compose software without a way to refer to the pieces. To support bindings, our interpreter needs internal state. When you define a variable at the beginning of the program and use it at the end, the interpreter has to hold on to the value of that variable in the meantime. So in this chapter, we will give our interpreter a brain that can not just process, but remember. State and statements go hand in hand. Since statements, by definition, don't evaluate to a value, they need to do something else to be useful. That something is called a side effect. It could mean producing user-visible output or modifying some state in the interpreter that can be detected later. The latter makes them a great fit for defining variables or other named entities. In this chapter, we'll do all of that. We'll define statements that produce output, like print, and create state, var. We'll add expressions to access and assign to variables. Finally, we'll add blocks and local scope. That's a lot of stuff in one chapter, but we'll chew through it all one bite at a time. We start by extending Lox's grammar with statements. They aren't very different from expressions. We start with the two simplest kinds. An expression statement lets you place an expression where a statement is expected. They exist to evaluate expressions that have side effects. You may not notice them, but you use them all the time in C, Java, and other languages. Anytime you see a function or method call followed by a semicolon, you're looking at an expression statement. A print statement evaluates an expression and displays the result to the user. I admit it's weird to bake printing right into the language instead of making it a library function. Doing so is a concession to the fact that we're building this interpreter one chapter at a time and want to be able to play with it before it's all done. To make print a library function, we'd have to wait until we had all of the machinery for defining and calling functions before we could witness any side effects. There's something in chat. Right. New syntax means new grammar rules. In this chapter, we finally gain the ability to parse an entire Lox script. Since Lox is an imperative dynamically typed language, the top level of a script is simply a list of statements. The new rules are... Okay, we've seen this. Yeah, so I kind of wonder if he's sort of alternating between parsing a new feature of the language and evaluating it. So because we've already done all the parsing, there's going to be a lot of like just talking about stuff we've already seen. All right, so the first rule is now program, which is the starting point for the grammar and represents a complete Lox script or REPL entry. A program is a list of statements followed by the special end of file token. The mandatory end token ensures the parser consumes the entire input and doesn't silently ignore erroneous unconsumed tokens at the end of a script. Which ours does, because we didn't put any OF. Right now, statement only has two cases for the two kinds of statements we've described. We'll fill in more later in this chapter and in the following ones. The next step is turning this grammar into something we can store in memory, syntax trees. There is no place in the grammar where both an expression and a statement are allowed. The operands of, say, plus are always expressions, never statements. The body of a while loop is always a statement. Since the two syntaxes are disjoint, we don't need a single base class that they all inherit from. Splitting expressions and statements into separate class hierarchies enables the Java compiler to help us find dumb mistakes like passing a statement to a Java method that expects an expression. That means a new base class for statements. As our elders did before us, we will use the cryptic name stumt. With great foresight, I've designed our little AST metaprogramming script in anticipation of this. This is why we passed in expr as a parameter to define AST. Now we need another call to define statement and its subclasses. This is eerily similar to the macro. Yeah. Run the AST generator script and behold the resulting stumt.java file with the syntax tree classes we need for expression and print statements. Don't forget to add the file to your IDE project or makefile or whatever. Parsing statements. The parser's parse method that parses and returns a single expression was a temporary hack to get the last chapter up and running. Now that our grammar has the correct starting rule, program, we can turn parse into the real deal. Okay, so parse is going to parse a series of statements, as many as it can find until it hits the end of the input. This is a pretty direct translation of the program rule into recursive descent style. We must also chant a minor prayer to the Java verbosity gods, since we are using ArrayList now. Okay. A program is a list of statements, and we parse one of those statements using the method, or this method. So statement is for parsing one statement. Okay, and because there's only two types of statements, it's simple. A little bare bones, but we'll fill it in with more statement types later. We determine which specific statement rule is matched by looking at the current token. A print token means it's obviously a print statement. If the next token doesn't look like any known type of statement, we assume it must be an expression statement. It's the typical final fall-through case when parsing a statement, since it's hard to proactively recognize an expression from its first token. Each statement kind gets its own method. First, print. All right. So yeah, this is kind of like calling the grammar rule to parse a particular kind. Since we already matched and consumed the print token itself, we don't need to do that here. We parse the subsequent expression, consume the terminating semicolon, and emit the syntax tree. If we didn't match a print statement, we must have one of these, expression statement. Similar to the previous method, we parse an expression followed by a semicolon. We wrap that expr in a statement of the right type and return it. Executing statements. We're running through the previous couple of chapters in microcosm, working our way through the front end. Our parser can now produce statement syntax trees, so the next and final step is to interpret them. As in expressions, we use the visitor pattern, but we have a new visitor interface, statement.visitor, to implement since statements have their own base class. We add that to the list of interfaces interpreter implements. Okay. Unlike expressions, statements produce no values, so the return type of the visit methods is void, not object. Okay. We have two statement types, and we need a visit method for each. The easiest is expression statements. We evaluate the inner expression using our existing evaluate method, discard the value. Then we return null. Java requires that to satisfy the special capitalized void return type. Weird, but what can you do? The print statements visit method isn't much different. Before discarding the expression's value, we convert it into a string using the stringify method that we introduced in the last chapter, and then dump it to standard out. Our interpreter is able to visit statements now, but we have some work to do to feed them to it. First, modify the old interpret method in the interpreter class to accept a list of statements, in other words, a program. Okay, so for each statement, we're going to try to execute it, and maybe we'll get a runtime error. This replaces the old code, which took a single expression. The new code relies on this tiny helper method, execute, which is just binding over the visitor pattern. That's the statement analog to the evaluate method we have for expressions. Since we're working with lists now, we need to let Java know. The main locks class is still trying to parse a single expression and pass it to the interpreter. We fix the parsing line like so. Okay. And then replace the call to the interpreter with this. Basically just plumbing the new syntax through. Okay, fire up the interpreter and give it a try. At this point, it's worth sketching out a little locks program in a test file to run as a script, something like this. It almost looks like a real program. Note that the REPL2 now requires you to enter a full statement instead of a simple expression. Don't forget your semicolons. Okay. Global variables. Now that we have statements, we can start working on state. Before we get into all the complexity of lexical scoping, we'll start off with the easiest kind of variables, globals. We will need two new constructs. A variable declaration statement brings a new variable into the world. This creates a new binding that associates a name, here beverage, with a value, here the string espresso. Once that's done, a variable expression accesses that binding. When the identifier beverage is used as an expression, it looks up the value bound to that name and returns it. Later, we'll add assignment and block scope, but that's enough to get moving. As before, we'll work through the implementation from front to back, starting with the syntax. Variable declarations are statements, but they are different from other statements, and we're going to split the statement grammar into two to handle them. That's because the grammar restricts where some kinds of statements are allowed. The clauses in control flow statements, think the then and else branches of an if statement or the body of a while loop, are each a single statement. But that statement is not allowed to be one that declares a name. This is okay if Monday do a statement, but this is not if Monday do a variable declaration. We could allow the latter, but it's confusing. What is the scope of that beverage variable? Does it persist after the if statement? If so, what is its value on days other than Monday? Does the variable exist at all on those days? Code like this is weird, so C, Java, and friends all disallow it. It's as if there are two levels of precedence for statements. Some places where a statement is allowed, like inside a block or at the top level, allow any kind of statement, including declarations. Others only allow the higher precedence statements that don't declare names. Okay. To accommodate this distinction, we add another rule for kinds of statements that declare names. All right, so a declaration is either a variable declaration or a statement, and the variable declaration is not a statement. Declaration statements go under the new declaration rule. Right now, it's only variables, but later it will include functions and classes. Any place where a declaration is allowed also allows non-declaring statements, so the declaration rule falls through to statement. Obviously, you can declare stuff at the top level of the script, so program routes to the new rule. The rule for declaring a variable looks like var_decl goes to var identifier equals expression, maybe semicolon. Like most statements, it starts with a leading keyword, in this case var, then an identifier token for the name of the variable being declared, followed by an optional initializer expression. Finally, we put a bow on it with a semicolon. To access a variable, we define a new kind of primary expression. Okay, so it could be an identifier now. That identifier clause matches a single identifier token, which is understood to be the name of the variable being accessed. These new grammar rules get their corresponding syntax trees. Over in the AST generator, we add a new statement node for the variable declaration. Okay. It stores the name token, so we know what it's declaring, along with the initializer expression. If there isn't an initializer, that field is null. Does he mean null or nil? Okay, means nil. Then
It's
we add
null.
an
And there is expression type for null. So probably null.
I thought Locks was calling it nil. That's yeah. So he was like specifically saying Locks has nil and Java has null. Then we add an expression node for accessing a variable. So okay, his AST generator thing, that just generates like the class definitions, right? Like it is he's not doing everything that we're doing in the macro, right?
Yeah.
Like yeah, this just gets the structure and then he still has to write the parsing logic. All right. Then we add an expression node for accessing a variable. It's simply a wrapper around the token for the variable name. That's it. As always, don't forget to run the AST generator script so that you get updated expr.java and statement.java files. All right. Before we parse variable statements, we need to shift around some code to make room for the new declaration rule in the grammar. Top level of a program is now a list of declarations, so the entry point method to the parser changes. All right. Calls this new thing, declaration, for parsing a declaration. Hey, do you remember way back in that earlier chapter when we put the infrastructure in place to do error recovery? We're finally ready to hook that up. The declaration method is the method we call repeatedly when parsing a series of statements in a block or a script. So it's the right place to synchronize when the parser goes into panic mode. The whole body of this method is wrapped in a try block to catch the exception thrown when the parser begins error recovery. This gets it back to trying to parse the beginning of the next statement or declaration. Okay. The real parsing happens inside the try block. First, it looks to see if we're at a variable declaration by looking for the leading var keyword. If not, it falls through to the existing statement method then that parses print and expression statements. Remember how statement tries to parse an expression statement if no other statement matches? An expression reports a syntax error if it can't parse an expression at the current token. That chain of calls ensures we report an error if a valid declaration or statement isn't parsed. Okay. When the parser matches a var token, it branches to var declaration. As always, the recursive descent code follows the grammar rule. The parser has already matched the var token, so next it requires and consumes an identifier token for the variable name. Then if it sees an equals token, it knows there is an initializer expression and parses it. Where's that? Yeah. Otherwise, it leaves the initializer null. Finally, it consumes the required semicolon at the end of the statement. All this gets wrapped in a statement.var syntax tree node, and we're grooving. Parsing a variable expression is even easier. In primary, we look for an identifier token. That gives us a working front end for declaring and using variables. Forgot what previous means. I guess that this is like a token class, an instance of the token class, so it'll have like the data in it. All right, all that's left is to feed it into the interpreter. Before we get to that, we need to talk about where variables live in memory. All right, I think I will probably, let's see how long this section is. I'll read through this environments thing, and then we can get back to looking at the parser and sort of take stock of what we need to do. So, environments. The bindings that associate variables to values need to be stored somewhere. Ever since the Lisp folks invented parentheses, this data structure has been called an environment. You can think of it like a map where the keys are variable names and the values are the variable's values. In fact, that's how we'll implement it in Java. We could stuff that map and the code to manage it right into interpreter, but since it forms a nicely delineated concept, we'll pull it out into its own class. All right, so environment.java. Environment contains a map from like variable names to anything. Object. There's a Java map in there to store the bindings. It uses bare strings for the keys, not tokens. A token represents a unit of code at a specific place in the source text, but when it comes to looking up variables, all identifier tokens with the same name should refer to the same variable, ignoring scope for now. Using the raw string ensures all of those tokens refer to the same map key. There are two operations we need to support. First, a variable declaration binds a new name to a value. All right, so define this name as this value. It just puts it into the map. Not exactly brain surgery, but we have made one interesting semantic choice. When we add the key to the map, we don't check to see if it's already present. This means that this program works. All right. Yeah, so shadowing. We've got shadowing. A variable statement doesn't just define a new variable, it can also be used to redefine an existing variable. We could choose to make this an error instead. The user may not intend to redefine an existing variable. If they did mean to, they probably would have used assignment, not var. Making redefinition an error would help them find that bug. However, doing so interacts poorly with the REPL. In the middle of a REPL session, it's nice to not have to mentally track which variables you've already defined. We could allow redefinition in the REPL but not in scripts, but then users would have to learn two sets of rules, and code copied and pasted from one form to the other might not work. So to keep the two modes consistent, we'll allow it, at least for global variables. Once a variable exists, we'll need a way to look it up. All right, so when you get a variable with a given name, you will see if it's in the map and return it if so. Otherwise, you throw a runtime error saying that it's not defined. This is a little more semantically interesting. If a variable is found, it simply returns the value bound to it. But what if it's not? Again, we have a choice. Make it a syntax error, make it a runtime error, allow it, and return some default value like nil. Blocks is pretty lax, but the last option is a little too permissive to me. Making it a syntax error, a compile time error, seems like a smart choice. Using an undefined variable is a bug, and the sooner you detect the mistake, the better. The problem is that using a variable isn't the same as referring to it. You can refer to a variable in a chunk of code without immediately evaluating it if that chunk of code is wrapped inside a function. What does that mean? You can refer to a variable in a chunk of code. Oh, I see. So it needs to parse like a lambda expression without that variable already being in scope. And then use, yeah, got it. If we make it a static error to mention a variable before it's been declared, it becomes much harder to define recursive functions. We could accommodate single recursion, a function that calls itself, by declaring the function's own name before we examine its body. But that doesn't help with mutually recursive procedures that call each other. Consider is odd and is even written in a terrible way. The is even function isn't defined by the time you're looking at the body of is odd, where it's called. If we swap the order of the two functions, then is odd isn't defined when we're looking at is even's body. Since making it a static error makes recursive declarations too difficult, we'll defer the error to runtime. It's okay to refer to a variable before it's defined as long as you don't evaluate the reference. That lets the program for even and odd numbers work, but you get a runtime error in print a var a equals too late. As with type errors in the expression evaluation code, we report a runtime error by throwing an exception. The exception contains the variable's token, so we can tell the user where in their code they messed up. All right. Let's see. Yeah, last little bit. So interpreting global variables. The interpreter class gets an instance of the new environment class. We store it as a field directly in interpreter so that the variables stay in memory as long as the interpreter is still running. We have two new syntax trees. So that's two new visit methods. The first is for declaration statements. All right. A visit var statement. If the variable has an initializer, we evaluate it. If not, we have another choice to make. We could have made this a syntax error in the parser by requiring an initializer. Most languages don't, though, so it feels a little harsh to do so in LOX. We could make it a runtime error. We'd let you define an uninitialized variable, but if you accessed it before assigning to it, a runtime error would occur. It's not a bad idea, but most dynamically typed languages don't do that. Instead, we'll keep it simple and say that LOX sets a variable to nil if it isn't explicitly initialized. Thus, if there isn't an initializer, we set the value to null, which is the Java representation of LOX's nil value. Then we tell the environment to bind the variable to that value. Next, we evaluate a variable expression. Okay, so visit variable. This simply forwards to the environment, which does the heavy lifting to make sure this variable is defined. With that, we've got rudimentary variables working. Try this out. A equals 1, B equals 2, print A equals B. We can't reuse code yet, but we can start to build up programs that reuse data. Okay. Yeah, I think I will stop reading there. Does anybody have questions or want to go back to something? Remember. Section ended on. Okay. It's pretty simple. Let me see. I am still sharing, right? Am I sharing
Yeah.
the screen?
Mhm.
Okay. For some reason, when I started recording, it stopped showing that I was sharing the screen. Let me I'll open up the parser code and we can kind of look at that. So let's see. Let me I think there's something simple we can kind of fix, which is the EOF thing. So I believe that if something doesn't parse with our parser, it will just it'll just produce like an empty program and then the list of unparsed tokens after, when it should say it couldn't parse because there wasn't an EOF.
Well, alternatively, we can run our parser and confirm that it produces nothing.
Yeah, that's fine. That's fine.
So for that, I made this helper function.
All right, I'm I'm curious, do you think there's any file reorganization we can at least do?
Well, we can try to move it out of the main.rs into lib.rs at least.
Yeah. Okay. That's gonna.
But this will result in a bunch more merge conflicts in my case.
Okay. Oh wait. Oh wait.
We can try to write something to evaluate the expression. So right now we can successfully parse algebraic expressions without variable assignments.
Sure.
And we can write parser. We have parser. We can write evaluator for that.
Okay. Yeah, that's probably a better idea. All right. So, sure. I'll do a test. Okay, that's an expression. We can still evaluate as an expression. And then what?
Check the chat. There is a function I'm using.
Parse. Okay. Put this in here. See what about the syntax.
So you call it first parameter as a string you want to parse. The second parameter is the parser. In our case, it's going to be expression : new. If it succeeds, it gets you the expression back. Otherwise, it panics. I made it so you can parameterize on parser, so I can test each individual parser bit.
Got it.
It complains about leftovers. It complains about failing to parse.
Let me find where, like the end of the parser stuff. Right there.
So first is, no, it's just 3 plus 4 or sample. Yeah. And parser is expression : new.
But this takes
without parents.
Oh, okay. So it's a parsing function is what
you
pass it. Got it. Okay. So then to evaluate it, we want to have some sort of evaluation method.
Well, probably it needs to be a function that takes an expression and takes a state. For now, state can be empty. And produces a new expression back, I guess. It's going to be either number, null, one of those.
Yeah. So it's what we need is the equivalent of Java's objects, right? So I don't think it's actually an expression. It's like whatever it means a value for us.
We don't have anything better than expression.
Okay. That's fine. Okay, I mean, so, but it's like specifically a primary, so it would be something like
we can factor out that bit from expression into separate enum. And do you remember what they use in the book for that purpose?
Yeah, they use a Java object,
Okay.
which is more general than we need. But
Yeah, we're not
a
going to do
runtime
that.
value is called an object. And maybe a value enum, like
Yep, that sounds reasonable, and make that part of expression.
sure. Okay. What are the values?
Number, string, bool, nil.
Okay. Is it actually useful trying to bake it into expression? Or do we want to refer to like an expression version of a number and then a value version of a number? Because like this would be like.
I think, well, we will have to assign value to some variable, and
Yeah.
assignment takes an expression. So unless you want to convert from value to expression, which we can do.
From value to expression?
Yeah.
I thought it's like at runtime. So we're going to parse it into an expression, and then at runtime, it will evaluate that into a value.
Okay, let's leave it separate for now.
Yeah.
You'll see how it goes.
I'll see how it goes. You already know how it's going to go. All right. Yeah. Okay, so yeah, this becomes a value. So, okay, so how does he do it in the book? Probably call eval on your left and right.
We pattern match an expression. No, we just pattern match an expression directly. We don't have left or right. Match expression. Fill in the branches.
Okay, sure, yeah.
Right click on the expression. It should be able to fill it for you.
I think we did this before. It's like not something I have in my LSP. But like, is there supposed to be a command for like fill in all the enum variants?
Yes.
All right.
It's not n, it's value n. Yeah. Identifier, we need to read it from state, but we don't have state yet, so we just panic.
Okay, sure. All right. But we have value nil. Okay. That I don't know. We haven't gotten to.
Yep. At that, we make recursive call to eval this expression inside. grouping is just parens. And that's it.
Okay. Why isn't it like that? For destructuring a
You need to get the destructuring working. You don't have an expression. What you pattern matching right now, it's just the names. You miss the expression colon part.
I don't get it.
There is no pattern number as such. It's expression colon number on line 1644, for example.
Oh, okay. Yeah. So and that's just because of like
Because
did we do
it.
it like this, or that's wrong to do?
That works, but that's not very good for
Okay.
compatibility.
That is fine.
You need to spend some time figuring out how to work with Rust Analyzer.
Yeah. Okay. So this thing, that's still not right. Okay, that's right. So as you're kind of destructuring it by unboxing. All right, and then I think I get how it goes now. It's like you don't need the type here. But it does evaluate it for you. Okay, so this should be eval left and then apply operator.
Eval left, eval right, and pattern match on operator and combine them.
Yeah.
You can use just left as a name.
Oh, sure. Yeah. Okay.
You need to get it working.
Yeah. All right. I'm just gonna actually find out how to do that. That seems like a good use of time. Rust Analyzer, all match variants. All match arms.
I think I've seen it pop up as the little light bulb on the left, but haven't seen it pop up on your screen.
I might have turned off that light bulb because it annoyed me. So let me let's see. What's the light bulb called? VS Code light bulb. Code actions. Suggest selection. Okay. Quick actions. It thinks I can do control plus or something. N plus. Sorry. All right. Yeah. Okay. There we go. I've looked up how to disable it, so I'm going to bring it back. Light bulb. There we go. There we go. Okay.
Here we go.
Thank you.
No problem.
Awesome.
All right. So
I think we have the pattern match on all three items, left, right, and operator. Because we can divide numbers by each other, but it doesn't make sense to divide string by string.
Right. So that's like, let me see how he actually organized it. Like if he had a function, like a helper function for adding, but throwing errors at the appropriate times. Okay, so check number. Yeah. So he put it into a separate check function for seeing if all of the types were right, I guess. So operator left and right. So this checks to see if they're both actually numbers. If they aren't, then you throw. Then the only reason you need to know about this is for the error message. Okay. So that's fine. I'll just make that helper function.
No, we can make a function from operator to a function that takes two expressions.
Sure. Yeah. So checker expert type. Okay. I guess this is a binary op, which takes a binary operator. Okay, sorry, I'm doing like C types. Op binary operator, and returns a function, which I'm not used to writing.
Okay, so capital F, impl. No, get rid of impl goes in front. Yeah, impl fn parents.
Because this is a trait. Yeah.
Yes.
Impl fn
parents in parents expression, comma expression.
Okay.
Capital expression.
So this is the signature.
Yes, arrow.
It's like a value.
Yeah.
Not. So you're not writing a checker. You're writing like the evaluator.
Yeah.
Okay. So.
Although it can be fallible, right?
Yeah, it's a result value. Or
we can panic.
Yeah. One of the things, this will go. I don't know if you've already hit this part, but it eventually wants you to print out errors from different statements to like print out multiple errors. So if you panic too much, you're gonna only hit the first error you see.
Yeah, I agree. Yeah, he talked about that in like, right. It's like in each there's a try catch on each declaration. So
yeah.
So right, we're just trying to get like some subset of it.
Literally just somewhere. Okay, yeah. Sorry.
No problem. Okay, so result value.
We have data type called result used in exactly one place, and it hard codes error message.
Okay.
Hard codes error type to boxed in error.
Yeah. Okay.
Okay. Yeah, so match up.
And then
fill in branches.
Okay.
So for minus, it's going to be
Well, yeah,
that's not going to work.
Yeah, we need this thing, I think, because most of them will share this check. And only a few of them will have their own special check for whether to reject. Or sorry, not that. This one, the binary one. I mean, I can declare it in there, I think.
It's not going to work the way we wrote it, because I thought about returning a trait object, but trait object for closures have different types, so we'll have to evaluate it.
Okay.
And then there is addition. Does it support string concatenation and number addition with plus operator?
Yeah, it does. So we have to break the pattern there.
Okay, so just the check is, maybe it's fine. We try one, try the other.
This seems like the thing to factor out.
I would return option F64 here. Option.
I'm not trying to evaluate, I'm just trying to figure out the types are right.
Yeah.
We can evaluate it after we verified.
Suppose you know the numbers. Next step, you will want to know what the values are.
You could do option of a pair.
Yeah. You might as well produce it right away.
Okay. All right. So let's think this through this. So which ones don't need numbers? All of these comparison things just need things that are truthy. And then these need numbers. And then this one needs numbers or strings. So his is truthy. So don't we need these same functions and then we just like compose them in a different way to get objects? I don't really see.
I don't think so.
Okay.
I don't see how this is truthy is useful.
That's how it knows whether it's valid as one of the options in the Boolean expressions.
But you will immediately want to know what the value was. So we need option with values.
So how are you saying that we're filtering to the right type? Using pattern matching?
Yeah.
Okay, that's fine. So where should we do the match? Here? Like you said.
Well, that's going to be a whole lot of things.
Yeah. Here.
So, no, I think we do it inside match operator. So when we have binary operator plus, we try to check if they are numbers.
Yeah.
Otherwise, we check if they're strings. Otherwise, we complain.
Okay, let's write this as just an example for how we do
Yeah.
this. So we're gonna match left and right here.
I think we're going to match outside. So I would write it as something like if let sum left comma right in double parens. If let sum capital double parens left right equals a pair of numbers. That's going to be a function call. A pair of numbers.
This?
Just pair. It's going to be a function call. Function name is going to be pair of numbers.
Oh, okay, got it.
You pass left and right.
That's a checker function?
Yes, it takes two values and produces option pair of numbers. Do stuff. Packet into value and return. Maybe we don't need return.
Sure.
Else if let sum left right pair of strings.
I don't think I need that else.
You do need else.
But I should return then.
Yeah. Also, you might want to configure your editor to perform formatting on safe.
It is. It's just I have all this shit that's not parsing.
I see.
I don't know why it's not doing.
I think it's not doing it.
No, it does though if it parses. It must. Okay.
Never mind. It's your homework.
Yeah, I'll get it. I'll get it.
So let's try to write those two functions, pair of numbers, pair of strings, and that's going to be enough fun for today.
Yeah. Is that correct?
No, those are F64.
Okay. Yeah. So it's doing the unpacking at the same time
Yep.
as, yeah, okay.
Can be simple match. You can ask it to populate. It really saves time on typing. We only care about the first line. That would be none.
I don't. Okay. Yeah. Yeah. Okay. So at this point,
double parens.
yeah. At this point, okay. I don't know why my formatting's not working. Totally should be. All right.
Maybe it was annoying you. And we decided to disable it as well.
It's definitely still erroring due to lack of expression being, or compile error on it.
Why would it? Shouldn't it do its best attempt at formatting, even though there's a failure? All right.
You'd hope, but it does its best. I
How
wish it could.
come can't we just replace, instead of writing this helper function, couldn't this just be like what we have originally?
Mhm.
Wait.
Like here.
You don't want to repeat this all over the place, and pair of strings does not belong to this function.
I know. Okay, so but so the reason to make this its own function is because we're going to reuse pair of numbers like all over the place.
Yeah.
Okay, got it. Cool. Okay, and then concatenate. Does Rust also do this? No. No way, right?
I think I can do something like that.
Missing match one.
I need to take reference from the second string.
Oh, this is why it's not formatting. All right. Okay. That
Yep.
unboxing the value, you're right. Okay, otherwise throw an error, right? Okay, did we make this entire thing? Time error. But I'll just use whatever he does. Oh, he doesn't do it. Where does he throw the error? Maybe he puts it in, yeah, he puts it in here. Operands must be two numbers or two strings. Okay. So yeah, we probably need another error type, right, for runtime error.
Yep. So I will try to merge my tests and my refactors, and we split it into parts. So it don't finished. Oh. Okay.
You want to check out his code? I'll stop
No,
recording.
that would be cheating.
Are we cheating? Yeah, I agree. All right, stopping the recording.